by taking a semicircle, which we're going to call the base. So that's sort of sitting on the table. So we've got a semicircular base. And then we're going to create cross sections that are perpendicular to the base, which is how all of our solids will be created. We're not going to create some oblique cross section. Our cross sections are perpendicular to the base. And they tell us that those cross sections are squares. In particular, so let's first think about, okay, this is one way to draw a semicircle. This is the second way to draw a semicircle. This semicircle has that equation because you isolate x to measure everything horizontally from the y-axis. That would be the equation of that red semicircle. Similarly here, do you agree that this is not a function of x? Right? It doesn't pass the vertical line test. It is a function of y, though, because it passes the horizontal line test. So as I've drawn it here, this says x is a function of y. So this would pass the horizontal line test to be a function of y. Whereas this one is a function of x because it passes the vertical line test. So we can write it as y equals a function of x. So where we are, semicircular base, we now have the equation for each of those semicircles. It's not going to matter which one we use. And then the key piece to this problem says cross sections are squares parallel to the diameter. You could draw cross sections this way, but this would be perpendicular to the diameter because the diameter is here in this one. Over here, the diameter is there. We don't want squares perpendicular to the diameter. We want parallel to the diameter. So those are our two scenarios. Either one is totally fine. Now here is the piece that really sends us for a slight loop. When we look at this model right here, when we choose that as our way to think about it, the square, this is, and we can call it the base or whatever you want to call it. So that distance, though, that's going to be one side of the square. That is a horizontal distance. Anytime we measure something horizontal, we find the right x, we find the left x, and we take the difference. Over here, our element is vertical. Anytime we find a vertical distance, we take the upper y coordinate and subtract off the lower y coordinate. So this is horizontal. So now I don't want the equation for this semicircle right now because I'm measuring a horizontal. I actually want the equation of this right-hand side. If I can find the equation of that right-hand side, so this guy, that will be measuring horizontally. So this edge, so from there to there, that is going to have this equation right there. That is going to be the equation of the right side of the circle. This x right here is measuring this horizontal distance from the y-axis. Right? So this guy's measuring horizontal. This guy's measuring vertical. So this red function of x is measuring from the x-axis up to the red curve. This function of y is measuring from the y-axis over to the orange piece. So how long is the base then if this right here is measuring from the y-axis over to here? How long is the base?
Twice that.
Twice that. So b is going to be 2 times this quantity right there. So that would be one side of the square. So if you wanted the area of the square, what would you do to that? Square that. Now let's turn our heads 90 degrees and come over here. If we're looking here and we now want, again, the length of this base for the square, so this square is coming right out of the board. We want this vertical distance. if we look right here, this vertical distance right there is a difference in y values, vertical difference. We need the upper y value minus the lower y value. So if we want that distance right there, this is now a circle, a piece that's in quadrant 1. The equation for that is this guy, y equals the positive square root of 19 squared minus x squared. So this y, this function of x is measuring from the x-axis up to that function. The base, though, for the square is this entire thing. So what will we do to that to get the length of the base?
Multiply by 2.
Double it. Multiply by 2. Or we could do this. The lower curve down here is the negative of the upper curve. Right? This function of x is just giving us this top piece right here. This is not defined. This is just giving us a value from the x-axis up. It's not giving us something down here unless we put a minus in front of it. So you could say, oh, the upper y value is that. And then all the way down here, the lower y value is that. This minus that also gives us 2 times the square root. So you could think of it either way. If this distance is 2, and you want to go all the way down to here, you could double it and say, oh yeah, that distance is 4. Or you could say 2 minus 2 is also 4. So you can take the positive piece and double it, or you can take the positive piece and the negative piece and do the subtraction, ending up with the same result, doubling that top piece. So same idea here. Our base is going to be 2 times that. With this one, your integral is going to have a dx, because your rectangles are vertical. This one, you would have a dy, because your rectangles are sideways. They're horizontal. So work on that one, see if you can get it. We can talk more about it on Thursday or after class. But that is the trickiest problem in that homework set for sure. I think it's in 6.3.
Yeah.
Sorry, 6.3. Okay, so let's go back to where we are. On Thursday, we left off with a slightly new strategy called the washer method. And so let's just review kind of the basic layout here. If we take this gray region R and we rotate it around the x-axis, we're going to get this solid object that looks kind of like a bowl opening to the right. Here is what one cross-section will look like. The cross-sections are going to be washers because of this little gap right here, which we're going to call the inner radius. The outer radius goes all the way up to the second curve. The inner radius goes to the first curve. The outer radius goes there. When that segment rotates around, it's going to create a washer because there's a little hole in the middle of it. So there is a representative cross-section, or you could call it a representative slice, because you can see that I've actually added some thickness to it. When we use the expression cross-section, that's flat. But then when we say slice, we've puffed it up a little bit. We've added some thickness to it, so then it becomes a miniature volume. So the washer is the cross-section. And then when we put a dx or a dy next to it, then it creates a washer with a little thickness, so it's got some volume to it. All right, so our concept is the same as with the disks. If we can find the cross-sectional area as a function, we integrate cross-sectional area, that's going to give us volume. So the area of a washer, you can think of the outer radius here. That's going to create a bigger disk. The inner radius is going to create a smaller disk. Take the big area, subtract off the small area. You get the area of the annulus, or the washer, as we say. The mathematical word for a washer is an annulus. And so we're finding the area of the washer. Outer radius squared times pi, inner radius squared times pi, factor out the pi. There is our area. We can simplify this a little bit, not a whole lot. Power to power Back to algebra, we multiply when we have power to power, so that's going to be x to the 2/4, which is x to the half, minus x to the 2. So there's our area. That is the area of the washer, and then we integrate area to get volume. So we are just going to integrate that. With respect to x, one of our basic geometric things that you have to get really clear is that the representative rectangle is perpendicular to the letter that you're integrating with respect to. So vertical element, dx. Horizontal element, dy. It's like it's always going to be perpendicular and sliding. So now our limits of integration, we're looking for an x interval right down here that represents the intersection points, the x coordinates of those intersection points. That one looks to be 0, and then we have to figure out that one. Let's come off to the side and do that. So we set our curves equal to each other. X to the 1/4 is equal to x. There's a couple of ways to do this. We can subtract and factor. It might feel a little funny factoring this, but you can do it. The other possibility is that in algebra you learned if you have a square root equation, square both sides, and then put everything to one side and factor. But you have to remember, if you square an equation or raise an equation to an even power, you can introduce extraneous roots. So you just have to double check at the end. So I think the easiest way is to raise both sides to the 4th power here. Pretty simple, raise each side to the 4th. So we're just going to sort of do this kind of thing. And now there should be that little bell that goes off because we raised each side. So that's a bell. So there should be a bell that, if we raise both sides to an even power, there could be extraneous roots. Not necessarily, but there could be. We just have to beware. And then we're going to subtract. Doesn't matter which direction you subtract. Then you factor. Then you use the 0 product rule. And we only have 2 answers there. Well, there's only 2 intersection points. There's no extraneous solutions here. It all matches. If we ended up with 4 answers there, but we only have 2 intersection points, then we'd have 2 extraneous. But that didn't happen. So we know that that's 0, and down here, that's 1. So we're now going to integrate our vertical integration element across this interval from 0 to 1. And the integration in this case is done with the power rule. So we add 1 to the exponent. 1/2 plus 1 is 3/2. We divide by that new exponent, which is the same thing as multiplying by the reciprocal. Add 1 to the exponent here, divide by the new exponent, 0 to 1. And we get a pretty nice looking problem. Plugging in 1 gives us 2/3 minus 1/3. Plugging in 0 gives 0. So we don't even really have to think about that. 2/3 minus 1/3 is 1/3. That is our volume. That will be our volume. So we want to distinguish between the problem that we were talking about at the first piece of class. We created the solid by defining what the geometric cross-sections were going to look like. We said we're going to stack squares next to each other. This is different. We're creating the solid by rotating a region. And if you rotate a region, your cross-sections are always going to be disks or washers at this point. We'll have some other things soon, but at this point, disks or washers. So let's go ahead and do another one of these. So we're going to find the volume of the solid. We're going to rotate this parallelogram around the x-axis. We're going to get some sort of thick cone-looking thing. Cross-sections will be washers because this gap right down here, when we rotate that around, it's going to create a washer with that as the hole in the middle. All right. So we need to identify the inner and the outer radius, which is done by looking at the graph here. This will be the inner radius, that vertical distance. So we would want this function to be measuring vertical distance, so we're going to isolate y. Oh, y is already isolated. We don't have to do anything extra. Nice. We like simple. This distance right here is the outer radius. Once again, that's going to be measuring a vertical distance, so however we present this function, we want to isolate y. If you isolate y, you're measuring vertical. If you isolate x, you're measuring horizontal. All right, so now we go to our basic geometric formula for the area of a washer. So that's going to be pi times the outer radius squared minus the inner radius squared. And so now we just have to identify and turn this generic formula into a specific formula with these two functions. So the outer radius, so it's a vertical distance. This is the y value for this curve right here. So x plus 2 is the y value. So we're going to put x plus 2 in here minus, now we have the inner radius here. The y value for this inner radius right there, the y value is this on the right side. That's x. So that's going to be minus that. And then we do our algebra. So we FOIL this out. We get some nice cancellation. We can even factor out a 4. And that is our area function. That's giving us the area of the washer at x. So we have an infinite number of washers stacked right next to each other. That tells us the area of each of those washers. If we wanted to just check, we could pick this left extremity, and we know that the radius of the washer right here, which is actually a disk, there's actually not a hole in this washer. What should the radius of that washer be right here if we rotate that?
2.
So the radius is 2. The inner radius is 0. So 2, finding the area of a circle of radius 2, that's going to be 4 pi. So if we plug in 0 over here, we should get 4 pi from our area predictor function here. Plug in 0, yeah, we get 4 pi. So that means that most likely we have the correct area function. And then to get our volume, all we have to do is integrate the area on the x interval. So we're looking over at our x interval right there. There's our interval of integration. They tell us to go from 0 to 4. So we know that that's a 4. So this integration has limits 0 to 4. We're integrating a polynomial, so we use the power rule. Power rule says add 1 to the exponent, divide by the new exponent. So we get x squared divided by 2 plus x, 0 to 4. Once again, plugging in 0 doesn't give us anything, so we're subtracting out 0. So 4 squared is 16 over 2 is 8, plus 4 is 12. 12 times 4 is 48. So as long as I did that arithmetic right, this will be our volume. Did I do the arithmetic right? 16 divided by 2 is 8. 8 times 4 is how many? Oh, no, but I had to add 4. Okay. 8 plus 4 is 12. Okay, I agree with it. Monday morning arithmetic on a Tuesday. Today's our Monday. Or at least it's my Monday. All right, so there is a pretty decent example of a washer method. Any question on the outer versus inner versus vertical rectangle, horizontal rectangle? There's only one thing to do, make it harder. Let's go sideways. Turning your head 90 degrees makes it harder for some reason. So now we are imagining the region being horizontally simple instead of vertically simple. So right here, you can't draw a vertical element and have the same upper curve and lower curve as you go across here, right? It's all mixed up. So you do not want to use a dx. You do not want to use a vertical integration element. You do not want to use a vertical rectangle. We want to use horizontal because no matter where you draw your horizontal rectangle, your horizontal integration element, you always have the same left curve and the same right curve. Doesn't matter where you draw that horizontal line. So that tells us dy. We're going to integrate with respect to y. That's what that tells us. And the process is the same as what we just did. The only difference is that now we are dealing with horizontal rectangles, so the inner radius and the outer radius are now functions of y. We want to be measuring horizontal distance, so we have to isolate the x. We want to solve for x for each of those functions so that we're measuring from the y-axis over. Anytime we find a horizontal distance, it's x minus x. The right x minus the left x. So we want to write both curves as x equals something, and that's what they're saying here. So they're going to call the first one x equals p, the second one x equals q. So these are just solving for x, for the outer radius and the inner radius. So let's take a peek at an example. So here we have a region. Clearly it's not vertically simple. We have to go horizontal. We can't go vertical because here, upper curve, lower curve. But if you draw it here, upper curve and the lower curve is now different than the lower curve over here. So we do not want to use a vertical integration element. So we're going horizontal. So this inner curve, that's just the axis here. Thank you. Right? So actually our cross sections are going to be what? Discs or washers?
Discs.
Discs, because that region touches the axis that it's rotating around.
No hole in the middle.
There's no hole in the middle. There's no gap between the y-axis and this region. So we are going to have a disc, and that is going to be the radius of the disc. That's a horizontal segment. If we want to know how long that horizontal segment is, we need to take this curve and present it as measuring horizontal distances. This curve right now is presented as measuring vertical distances. Y equals natural log of x. If we want to represent horizontal distances, we isolate the x. So we do our algebra. And now we have the x value of the right side of this rectangle. This x value is e to the y. So this, you can think of this in multiple ways. You can say, okay, I've isolated x, so now we're measuring horizontal. You can say you've written x as a function of y. Right? If you have y on the right, y is now the independent variable, and you plug in y's to get x. So you can think of it in a couple of ways. I think of this as the x value of this curve right here. So that tells us then that our area, it's the area of a disk. We know our generic formula is pi times the radius squared. So we do pi, and then we do our radius, which is e to the y squared. So pi e to the 2y. And here's where you have to do the gut check. You have to say, okay, area is now a function of y. Does that match your picture? Yes, because we have a horizontal rectangle. That means the thickness of this rectangle is dy. And when we put a dy right there, it matches. We have y's and y's. No commingling of x's and y's. So our volume is the integral of this area function. Now we just need our limits of integration. Well, they tell us. They said that our upper function is y equals 2. Our lower function is the x-axis, y equals 0. So we know that this is 0 and 2. So that's given to us in this case. Didn't have to do any simultaneous solve. Now we have to remember how to integrate an exponential function. Remember, exponentials are completely different than polynomials. Polynomials, we have that little routine. Add 1 to the exponent, divide by the. That's not for an exponential. For an exponential, the routine is the integral or derivative of an exponential is itself. And then you have to do a chain rule or reverse chain rule thing. So when we integrate here, the integral of an exponential is itself. We always start with that for integration. But we notice that the exponent is not just y, it's modified. So we have to use the reverse chain rule for integration here. Do notice that this is linear. The reverse chain rule only works when you have a linear substitution. And then the effect of the reverse chain rule is that you divide by the derivative of that exponent. So that's how we integrate an exponential. Itself divided by the derivative of an exponential, derivative of the exponent, as long as that exponent is linear. And then we have our limits of integration. When I plug in 0, will I get 0 like we just did in the last two examples? No, because an exponential has the variable in the exponent position. If you plug in a 0 there, you get e to the 0, which is 1. Okay? So let's go ahead and plug stuff in. I'm going to factor the pi over 2 out. So I'm just keeping this out in front. So now I'm going to plug in the limits just into the e piece of this. So we will have e to the 4 minus e to the 0. And of course, e to the 0 is 1. So we have e to the 4 minus 1. So there is the volume. Okay, so here is that solid object right here with that region rotated around, creates that wild looking thing. And each cross section is a disk, which we can see right there. So that's a representative disk, which then turned into a representative slice when we did the dy. dy is the thickness of that disk there. That slice. All right, let's try one more around the y-axis. So same concept, we're going to rotate that region around the y-axis. It's going to create like a thick cone type thing. And clearly it's not vertically simple. If you start scanning a vertical element across here, you see that, ooh, at this transition point, the upper curves are different. So it's not vertically simple. But if you scan a horizontal element through, left curve stays the same all the way throughout, right curve stays the same all the way out. So we want to go with a dy, with a horizontal rectangle. Now, same basic scenario as before. We think about our cross-sectional shape. When we rotate that around, we're going to get a washer, because there's a gap between the axis of rotation and this region. So we're going to have to identify two things. We need to know the inner radius, and we need to know the outer radius. Both of those are measuring horizontal off the y-axis. Anytime we measure horizontal, we are thinking about x's. So we want to write the inner curve in a way that we've isolated x. So the inner curve is this one. We are going to isolate x. So x is going to be y over 2. So the inner radius is y over 2. We've got to solve it for x. This one is essentially solved for x. We just have to sort of reverse it if we stick with our reading from left to right thing. So this tells us that our outer radius is y. Y is the x value of the right curve. Y over 2 is the x value for the inner curve. So the area of our generic washer is pi r outer squared minus r inner squared. So we will have pi multiplied by our outer is y, and then we have to square it. And then our inner is y over 2, and we have to square that, so we get y squared over 4. So there is the area of our washer. Those happen to be like terms, so we could put a 4 over 4 here. We're going to get pi multiplied by 3y squared divided by 4, which we normally would probably write as 3/4 pi y squared. All right, any questions up to that step? So here's where we do our little gut check. We have our area as a function of y. We look at our picture. Oh, yes, we have a horizontal rectangle, so we know the thickness is dy. When we put a dy next to this, that matches. We have the letters lining up, dy and y. So
we're just subtracting that empty space left of the shape from the x-axis, or the y-axis.
From the y-axis,
in this
yep.
case, from the shape itself, and
Yep.
that's going to be, we're taking that area.
So this is the inside of a donut, essentially,
Yeah.
right? So this is the hole. Yeah, we're subtracting off the hole. The area of that hole is being subtracted off. Yep.
Now I get what.
You get the visual?
Yeah.
So volume will then be the integral of area. So we have 3 pi over 4. The integrand is y squared. Then we look at our picture, and they've actually told us that we're going from 0 up to 6. So those are our y limits of integration, 0 to 6. And when we do this integration, we'll end up with y cubed divided by 3 from 0 to 6. So plugging in 0 again is not going to give us anything. We have a little bit of cancellation here with the 3's. So we're going to end up with pi divided by 4 multiplied by 6 cubed is 216 minus 0. Let's see, 4, does the 4 go into there? That's 108. Yeah, 4 should go into there. So it goes into 21 5 times. And then 4, so 54 pi, I believe, if that arithmetic is correct. That'll be our volume. All right, any part of that you want clarification on? So a lot of these volume problems are boiling down to pretty simple geometry. The area of a washer, the area of a disc, the area of a square we've had, area of a triangle. So yeah, definitely need to have some of that geometry down pat.
Oh, hey, could I take a quick picture of that? I didn't quite get that last the answer to that last question.
I think 54 pi.
Let's see.
So, you ready to try one? You look amped. Amped! All right, so why don't you all try this one? So, I've done a pretty thorough job of identifying each of the pieces. Confirm in your mind that you agree if we're going to take this square root of x with x equals 4 in the x-axis, y equals 0 is the x-axis, and then we're going to rotate it around the y-axis. Just make sure that you agree that our inner is where it is, our outer is where it is. Make sure it makes sense, and then find the volume. There, we can see everything. Let me know if you're wanting a nudge on how to start it. I'll give you a hint, the cross sections are washers. So we're going to create that funnel looking thing. Yeah, it kind of looks like that ride at Waterworld, that toilet bowl ride. Except that the toilet bowl ride has a hole in the bottom. Here you would just be stuck. Maybe I'll take roll while you're straining your brains.
That's fine.
Anna Karina is here. Henry.
I got here. It depends on which.
First Henry.
Which Henry? You
There's
talking
only one
about?
Henry now.
Oh, did one of them drop?
Was it you?
No.
Oh, okay. So this is the one that dropped, right? Because your last name is Griegar.
Yes.
So Henry Burton has vanished. Allie?
Didn't miss that much, did I?
Cole?
Here.
Richard? Hayden? Other Henry? The only Henry now? And Daniel? Kaylee? River? Harold? Sam? Ari?
D to the fourth? Is that really like units? That's what I got. You're making do E to the 2, E to the 4.
John? Paul? Walter is out sick today. Sean? Shelby is out sick today.
It was probably supposed to be.
Connor?
Yeah,
JoJo?
Here.
I'm gonna do it this way anyways.
Corbin?
This will be simplified.
Mia? Zach? Landon?
Here.
And Link. All right. So our cross sections are washers. Yeah.
Is it supposed to be the natural log of x or is it the square root of x?
Well, that's a great question. Does that look like the natural log graph?
That does not.
That does not look like a natural log graph because the natural log would go through 1, 0. So this, and it tells us square root of x error. Yeah, this is an error. I just finished these notes at the end of last semester, so this is the first run through.
Okay, so.
So I am psyching you out right off the bat. The first problem I give to you, right? Oh man. Now let me just say, if we were going to isolate the x here, what would we end up with? If that function was actually this curve?
E to the y.
E to the y. Yeah. Oops, so sorry about that. So y equals square root of x. Yeah. I better go edit. All right. What do we get when we isolate x? Y squared. Thank you. So x is going to be y squared. So x equals y squared. And the other curve is already presented as an x value, so we're fine there. So the area of our, it's still a washer. That hasn't changed at least. It's just that our inner function is going to be a little different. So the outer function is what?
4.
4. And it's 4 all the way through, right? It's just a constant. And so then we square that. We're going to have 4 squared or 16. We'll write it as 4 squared just to reflect that formula for a moment. And then our inner is going to be y squared, and that will have to be squared. which will give us pi multiplied by 16 minus y to the 4th. Now, if this was natural log of x, we would have x equals e to the y, and if we squared that, it would be like that last example where we get e to the 2y. So I'll go in and edit that picture. Okay, that is our area function. And then we're going to find the volume by integrating the area. We can factor the pi out, and we are going to have this. And then our limits of integration. So we need to know where this square root function intersects this vertical line, x equals 4, and what would the y value of that intersection be? So this is our integration interval over here. What is this y value right there? What does that have to be? 2. If this x value is 4 down here, if we plug in 4 into that function right there, the square root of 4 is 2. So this y value is going to be 2. So we're going to go from 0 to 2 along the y-axis. So that will give us this. And then we can do integration. Once again, we're integrating a polynomial. So integrating a polynomial, we use the add 1 to the exponent, divide by the new exponent algorithm. Once again, we see that if we plug in 0, we get no volume from that. But if we plug in the 2, looks like 32 minus 32 fifths. I'll factor out the 32 here, giving 32 pi, and then 1 minus 1 fifth. Well, 1 minus 1 fifth is 4 fifths. No common stuff here, so we get 128 times pi divided by 5. That will be the volume. Make sense? So what you got? A few people?
Getting there.
Getting there?
Good.
Getting there? Blowing out the cobwebs? Yeah. No one was doing a lot of integrating over the winter break, eh? All right. So, now that you have that mastered, let's up the ante and create a random axis of rotation instead of a coordinate axis of rotation. So, we've got this region. 1 minus root x, y equals 1 is this horizontal line, x equals 1 is this vertical line. And we're going to rotate not about a coordinate axis, but we are going to rotate about the line y equals 1. So all the geometry is the same. All we have to do is be careful. Vertical distance, upper minus lower. Horizontal distance, right minus left. That's really all we need to remember. So this region rotates around. It's going to create this nose cone looking thing. Because the region rotating around is touching the axis it's rotating about, there's no gaps. So our cross sections are discs. So if we drew a random vertical element right there, there's our random vertical element. Here's that random vertical element. When it rotates around, it's creating that disk. That's the radius of the disk right there. Everyone agree that that would be the radius of the disk? If this region is rotating around, whatever that distance is, radius is just a distance, that distance is the radius. So we come to our generic formula. The area of a disk is pi r squared we are using a vertical integration element here. Upper y minus lower y. Okay, that's how these have already been presented. This upper curve has been presented as a y value. This lower curve has been presented as a y value. So this distance is just the upper minus the lower. So we're going to take the upper y value, which is constant. It's just 1. We're going to subtract off the lower y value, which is a 2-termed expression. So I'm going to put it in parentheses because we'll have to do a distribution. And then we're going to square it. So the radius is the upper y minus the lower y.
I'm kind of wondering, like, why is that the upper versus lower? Like, if it was just a flipped image, I feel like the area would, or the volume would still be the same.
So if this is at 3 and this is at 1, and you do 3 minus 1, you get a positive 2. But if you did 1 minus 3, you would get
A negative.
negative 2.
Yeah.
So the radius has to be positive, and it's built into the algorithm. If we just do upper minus lower, it's automatically going to be positive. Everyone agree? If you do upper minus lower, it has to be positive. If we do lower minus upper, we'll get the same magnitude, but it will have a negative sign in front. We don't want that. Now, the fact that we're squaring it could work. You know, we could have two negatives could make a positive type of thing, but if we, anytime we see a vertical element, if we just do upper minus lower, it's going to work out fine. Anytime we see a horizontal, do right minus left. It doesn't matter where it doesn't matter where the axes are. Just always do upper minus lower or right minus left, and it will work. So when we do that, that's going to be.
We don't need to worry about doing things backwards.
Yeah, we don't have to try to do something backwards to undo the geometry or something like that. We just have to stick with the right minus left and the upper minus lower. Here we get some nice simplification. This is all going to turn into pi times x. So that'll be the area. Errol, question? So that is the area of the disk. And we can check. If we look at the degenerate disk right here, it's not really a disk, it's just a point. Right? So when we rotate around, the area of that degenerate disk should be 0. So this x value here is 0. If we plug in x equals 0 there, we get 0. So it predicts the area correctly there. If we look over at the far right, here the radius is 1. So our area function should predict that the area is pi times 1 squared, which is pi. So let's see, if we plug in 1 for that x, yeah, we get pi. It's measuring the area of that disk at the far right of our region. So now we're good to go for volume. Once we have our area function, all we have to do is integrate that area function on the interval. And we're integrating on the x interval, right? The x's are going from 0 over to 1. That'll give us our volume. So the integration interval, again, is always perpendicular to your rectangle. So we're looking down here. For all the x's between 0 and 1, we are going to have these disks that are stacked up next to each other. And so we're going to get x squared over 2 multiplied by pi. From 0 to 1. And we're going to end up plugging in 1 gives us a half, so we end up with pi over 2 minus 0. You don't have to put the minus 0. That will be the volume of that nose cone. So integrate area to get volume. Any questions on the ideas? Yeah.
So it's not 0 to 2 of the whole guy. It's just 0 to 1.
So when we ask ourselves the integration interval, we look at imagining all the possible disks. So here is a possible disk. Here is a possible disk. Here is a possible disk. The rightmost disk would be right there. So we're if we think in terms of small three-dimensional, not disks, but little tiny flattened cylinders, so slices, we're thinking of we're adding up the volume of each of these slices across from x equals 0 to x equals 1.
I'm thinking of it on the image on the right, where
Yep.
it goes all the way up to 2. Is like
Right. So that's the solid goes from 0 up to 2, but aren't the slices going from 0 to 1 on the x-axis? If we're integrating with respect to x, we're always going to be looking at the x interval. If we are integrating with respect to y, if we had a dy, then we'd be looking along the y-axis. But we are looking along the x-axis. And so this little radius that I've drawn here is going to draw a circle, which creates a disk that's about like that. And this one creates a disk that's about like that. But the area of the disk is going to be determined by that distance right there. And then we are going left to right. Does that make sense? Like if you're adding up rectangles that are going left to right, the area of the rectangle is sort of determining the height. The area of this disk is determining the height of that disk, but we don't care the diameter of the disk, however you want to think of it. That's not mattering though, because when we put this distance into this formula, it creates the area. We are getting the full area of that disk, right? And then we're going to add up all those disk areas across from left to right. But we're adding left to right, which means we go down to the x-axis and figure out what those 2 points are. Does that make sense?
Yeah.
The arithmetic on this one was kind of simple, so I think it's kind of nice just that I'm probably going to like almost circle this in my little notebook so I can refer back to it. It's like because the arithmetic is so simple, you're almost focused just on the process, and just to remember that this might be a good little model right there.
100%. Yeah, the functions here were simple enough that you can really just try to focus on that geometry, which is a struggle, right? All these things are very visual, and so we've got algebra and Calc 1, you don't really train your visual brain quite as much. Trig does, but so we have to try to train our brain. Okay, so here's another one. Stop moving. Okay, so square root function. And then x equals 0, y-axis. Y equals 2, horizontal line. So there's our region, our bounded region. And now we are going to be totally crazy and rotate around this line over here. That's going to be our axis of rotation. We're going to go around that. Okay. We are going to choose, this region is both horizontally simple and vertically simple, right? You could slide a vertical element all the way through and have a common upper and common lower curve. But if you had a vertical integration element and you rotated it around this vertical axis, would you get a disk or a washer? No, what would you get? If this is your axis of rotation, and you take a vertical rectangle and you rotate that around, what are you going to get?
Straws.
If it was the XY.
Did you say a straw?
Well, that's kind of a no. That's
It's a straw. Another word for a straw is a cylinder. Yeah, right? So if you have this as your axis and you take this vertical thing and rotate it around, you can think of it as a big straw, or mathematically we would call it a cylinder. Yeah, so we will get cylinders. So we've only done disks and washers so far. We are going to learn, though, in the next section, that we could actually create cylinders and do a very similar type of thing where you find the area of the cylinder and integrate it. That's going to be called the shell method. So important to sort of think about that, though. If you want to get a disk or a washer, your rectangle, your integration element here has to be perpendicular. Right? The only way you're going to get a disk is if that's perpendicular, right, to get a disk, and then a gap to create a washer. If they're parallel, you're going to get a cylinder. Okay, so we are going to get washers. So let's find the area of our washer. That's pi multiplied by the outer radius squared minus the inner radius squared. Okay. All right, now again, if we stick to our basic principles, right minus left for a horizontal distance, we can do this. So we start at our axis of rotation. We start moving towards our region. This first curve that we meet, that distance right there, that is going to be the inner radius. Right? The inner radius is always from the axis of rotation to the first boundary of the region. We keep on trucking the distance from here, trucking through the first curve and hit the second curve. That is going to be the outer radius. Okay? So now we say to ourselves, let's take our generic formula right there, and let's replace the r sub 0, or the r sub o, and the r sub I. Let's replace those. So we come over here. Okay, outer radius is this distance. This distance is horizontal. So I take the right x and subtract off the left x. The right x is 4. The left x is 0. And you can see, no matter where you draw your horizontal rectangle here, this distance is always 4, right? Because this is vertical. We're essentially saying, oh, what's the distance between this vertical line and this vertical line? 4. That is the distance. So we're going to have 4 quantity squared minus. Now, again, well, it's horizontal. The right x is still 4. The left x, okay, we've got to look at our curve. What is it? Y equals square root of x. That is not an x value. That's presented as a y value. That's measuring vertical. If we want to measure horizontal, all we do is isolate the x. So we come in here and make that x equals y squared. We've now isolated the x. This function is now measuring from the y-axis over the right x minus the left x. So 4 minus y squared, quantity squared. That'll be the formula for the area of our washer. So we're going to have 16 minus 16. We distribute in here, we're going to get 8y squared with a negative, but negative is positive, 8y squared. So then this is going to be plus y to the 4th, but we distribute the minus, so we get minus y to the 4th. So that'll be our area formula. Volume is the integral of area. dy is our letter of integration. That's the thickness of the washer that we're going to get, dy. And now the y's. So now we're looking at y's. We don't care that this thing rotating around goes all the way out to 8. Doesn't matter. This formula that we have right here takes all that into consideration. If we look at the washer that's created right here, it goes all the way around. The area of it is predicted by that function right there. But we have all these stacked washers. That formula finds the area of each of them. And so what should the limits of integration be? 0 to 2. Right? Because these washers are stacked with respect to y. So there's a washer at 0, washer all the way up to 2. So that formula builds, the area that goes all the way out to 8. But the y's only go from 0 to 2. We use our polynomial integration techniques. So we're going to have 8/3 y cubed minus y to the 5th over 5, or 1/5, however you want to write it, does not matter. 0 to 2. Plugging in the 2 is going to give us 8 times 8 is 64. So that'll be 64 over 3. Minus 2 to the 5th is 64. No. 2 to the 5th is 32. 32. 2 to the 4 is 16. 1 more 2 gives 32. Plug in 0 gives nothing. So we have that. I'll factor out a 32 just because it might make the math a little simpler in here. So if we factor out the 32, we're going to get 2/3 minus 1/5. Those will be a little easier to combine without that 32. So we'll have 32 pi, common denominator of 15. We're going to have 10 minus 3 in the top. So let's see, no common factors between the 32 and the 15, so we know we're going to end up with a 15 at the bottom. And then this is going to be 7 times 32. So 7 times 30 is 210, plus 7 times 2, which is 14, so 224. And then a pi. All right, so we've now seen a second example where we're rotating around a random vertical line. But our general principles are the same. Right minus left, upper minus lower. If we can keep that straight, we're good. Ready for a break? That was enthusiastic. Yes! All right, let's take a break. 10 minutes. 10 minutes to regain composure. Or to ask questions. Let me pause this. Does not want to come up.
I don't know, I feel like
That's weekend for you guys.
So, okay, let's find the volume of a torus, aka a donut. This is going to involve circles and semicircles again. So if you're struggling with that whole semicircle versus circle thing, go look at that review page under the chapter 6 and 7 review. That last slide gives you a little extra reinforcement on how to deal with semicircles. So the idea here is that we are going to take this circle right here, that dark greenish circle, rotate it around the y-axis, and it's going to create our torus, all right, our donut. And we are going to use horizontal integration elements here because if the axis of rotation is over here, the horizontal integration element, that's going to rotate around and create what object? We rotate that red element, that red horizontal. It's going to create a washer, right? If we drew a vertical integration element there instead of a horizontal and rotated it around, it would create a cylinder, right? If they're parallel, it's going to create a straw. That's going to be our new geometric object, the straw. Okay, so that's going to create a washer. Now, this is horizontal. That means we need to have functions of y, aka x values. We need to solve for x for each of the curves. If we want to know how long this distance is right here, we would need to subtract this x value from that x value if we wanted to know how long this chord is. All right, so that means we're going to need to find this left point as an x value and this right point as an x value. The equation of this big circle here, recall that the center is at 3, 0, and they told us that the radius was 2 up in the problem. So this is the equation of this circle. You shift the horizontal direction 3 units to get to the center. You shift the vertical 0. So it's x minus 3, y minus 0. Okay? And then the radius squared on the right. Now, if we want to find the equations of the two semicircles here, we have to isolate x. So I'm going to subtract off the y squared, take the square root, and then add the 3. So this is going to be the right half, and this is going to be the left half. And when you take that square root, you get a plus or a minus, and it's going to create the right half or the left half. Just like, you know, if you have like a, if you had a parabola, y equals x squared, right there, y equals x squared. If you solve for x, you get plus or minus the square root of y. So this half would be x equals the positive square root of y, and this half would be x equals the negative square root of y. So if you isolate with a square root, you always are going to get a positive or a negative when you take a square root. So that tells us what the right x value is and what the left x value is. So the inner radius is going to be this distance right here from the axis of rotation until you hit the first curve. There's the inner radius. And the outer radius is going to be from there all the way across to there. That is the outer radius. All right. We are dealing with a washer. Bless you. Area of a washer, pi times outer radius squared minus inner radius squared. So the outer radius squared. Okay, bust out the algebra. Here we go. There's the outer radius right there, right, all the way across. And we have to square that. So we have 3 plus the square root, and that whole quantity is squared. It's the outer radius squared. Now we have to subtract off the inner radius squared. So inner radius squared. The inner radius is the distance from our axis of rotation over to the orange half of the circle. That's given by this, 3 minus, but the whole thing is squared. And like always, Calc 2 has lots of algebra. We have to be able to FOIL. Foiling looks a little more complicated all of a sudden. But when you FOIL, the 3 gets squared and you get a 9. To get the middle term, you multiply a times b and then double it. So you're going to get plus 6 square root. And then when you square the last part, the square root just goes away. So you get that. So remember, if you have a plus b quantity squared, this is a squared plus 2ab plus b squared. That's called a perfect square trinomial. All right, now let's do it again. So minus, let's keep the parentheses in here because it's going to get messy. So let's just square this, and then we'll distribute the minus afterwards. So again, one of those should be negative, though. This is the outer radius, which is positive. The inner radius over here, that should be a negative, right? Right there. That should be a negative because we're using the orange function.
Yep.
The inner has the minus. OK, so when we go to square here, 3 times 3, square that. Now the middle term here, here's the a, here's the b. When you double it, you get 6, except that it's negative. So negative square root, 4 minus y squared. And then when you square the end here, we're going to square all that. We're going to end up with the exact same thing we ended up here. When we square this, we get 4 minus y squared. So a minus b squared is a squared minus 2ab plus b squared. All right, so any questions on that perfect square trinomial stuff? Do you see how you square those things? So it's first squared, and then either plus 2 or minus 2 times ab, and then plus b squared. So b is this. When you square it, it's still plus. The b does not include the minus sign. So if you're thinking about identifying a and b, this is a, this is b. This is a, this is b. All right, so then we distribute the minus. Notice a little cancellation. Yeah, maybe we'll do some cancellation instead of writing it all out, Because if you distribute the minus, you get a negative 9, so those two 9s are going to cancel. When we look over here, this minus is going to make this 4 negative. This minus is going to make this y squared positive. That's going to wipe out this whole thing right here. Those are going to wipe out. When the minus distributes, you're going to get negative 4. There's a positive 4. You're going to get a negative times a negative, a positive y squared. There's a negative y squared. They'll cancel. So the only thing that's going to live will be that square root stuff. Minus and minus turns it into a positive. So how many of those square roots do we have? 12. We get 12. So that is the area of the washer at a height of y. And you can see that if you're up here at 2 or down here at negative 2, those washers have no area. So if you plug in 2 or minus 2, you should get 0, which you do. You get 0 if you plug in plus or minus 2 for the y. And the biggest washer that you get is going to be right in here, where the outer radius is 5 and the inner radius is 1. And if you do the math, that would match.
On that problem right there, is that left going to be bracketed
Here,
right above it?
here,
Should it be two? Okay. So you don't. Okay, you don't have to bracket it separately.
no, so we have this is the first part here, this is the outer radius squared, and we subtract off the whole inner radius squared, so we need these parentheses. And then, yeah. Okay, now here's our problem. We can write down the next step very easily. The volume is going to be 12 pi multiplied by the integral of the square root of this. And what are the y's going to do? They're going to go from where to where?
Negative 2 to 2.
Negative 2 to 2. Could we use symmetry? We've seen that having 0 as a limit of integration is always convenient. So certainly this is true. Is there a way that we could make that 0?
Yeah. Like you double it and then 0.
So if we double it and go from 0 to 2, that would also work. All right. Now, does anyone have a clue as to how to integrate that? Every idea that you have will be wishful thinking.
It's an identity? Is that what you're
It's not quite an identity. Once we get into a technique called trigonometric substitution, we will actually be able to write this using an identity where we turn the y into a trig function. Then we can get there. But at this stage, the only technique you really have for integration is substitution. And if you want to substitute something, the choice would be to take whatever is, inside the square root or in the exponent or in the angle. And whatever you choose for your substitution, the derivative of that quantity has to be somewhere, outside of that. So the derivative in here is negative 2y. So in order to integrate this with substitution, there would have to be like a y out here. If there was a y out there, you could integrate it with substitution, with u substitution. But at this stage, we do not have a technique to integrate this. But there are times where we use calculus to find area because we don't have a geometric formula for the area. Right? Like almost all the problems we've done so far, we've had these weird regions that we have found area for, and we needed to use calculus because we don't have some geometric formula for the area under a parabola or something. The opposite is also true. There are times where the calculus is too hard, but we might have a geometric formula. You look small. So there are times, if we can figure out what the geometry of this integral is, that could help us. So let's think about it. What is the geometry of this integral? So this is a function of y in here. So that function is x equals this. Right? That's that function. Okay. What is that? This is the right half of a circle of radius 2 centered at the origin. That's what that is. And if you weren't sure what it is, you could say, oh, let's square both sides, add the y's. Right. This is a circle of radius 2, but if you isolate x and choose the positive square root, you are generating the circle of radius 2 that is centered at the origin, and you're generating the right-hand side. This is x equals the square root of 4 minus y squared. Right? That's what that is. If you take the positive square root, you get the right half. If you took the negative square root, you get the left half. So this says we want the area under the curve, but if we're integrating with respect to y, that means the area between the curve and the y-axis. It's not under. So we want the area under this curve from y equals 0. Y equals 0 is right here to y equals 2, which is right there. So that's what this integral is asking. It's saying, what is the area beneath this curve, and by beneath, again, we mean this way, from y equals 0 to y equals 2. So this integral right here, all it's asking for is the area of the first quadrant of a circle of radius 2 centered at the origin. That's what that integral is representing. This whole integral is that area. Because that's what an integral is. It's the area beneath the curve. So we look at the curve, we graph the curve, we double check our limits of integration, only go from 0 to 2. If this went from -2 to 2, it would be asking for the whole semicircle, which is twice the area of one quadrant. So we know what this area is. This area is 1/4 pi r squared. It's one quadrant. I keep wanting to say octant. It's one quadrant. So it's pi r squared. The radius is 2. Right? The radius of that circle is 2, so the area of the circle is 4 pi. So if we want the area of just one quadrant, we divide that by 4. So the area right here is just pi. Area of one quadrant. So this integral up here can be replaced with pi. And this is our volume, 24 pi squared. That is the volume of our torus, 24 pi squared. If someone in this classroom earlier was talking about physics, there is a very clever, if they didn't mention, this is their fault now. There is a very clever physics way to do this problem that is fun physics, not trash physics. And we can take this thing here, and as that disk rotates around the axis, there's a very clever way called the theorem of Pappus to find the volume. You can say, hey, what's the center of mass of a disk? So if the disk has uniform density, what's the center of mass?
It's going to be around the axis of rotation.
But the center of mass for the disk will be its center.
Yeah.
Right? The center of mass, the average point is the center. If we find the average point, aka the center of mass, and figure out how far the average point travels, and then multiply that by the area of our generating region, we will get the volume. So if we find the average point here is the center, and if we find out how far the average point travels, that would be the circumference, and then multiply it by the area, it's kind of like if you had a rectangular box, if you find the area of one cross section and then multiply it by the height, that's the idea, The circumference is acting like the height, where we're going to multiply that
So
by.
basically, you're taking the center point of that little circle there, making doing the rotation. You get a circle, and then you're multiplying the length of that circle by the area of the
Of the generating region.
Yes.
Yep.
Okay.
So this point here is 3 units away, so 2 pi r will be 2 pi 3. So this is going to be the distance traveled by that center point, right? It's the circumference of a circle of radius 3. So that's how far, that's circumference, multiplied by the area of this circle. So this is circumference, right there. And then this is area, right here. This disk right here is area 2, so that's pi times 2 squared. So we get 6 pi multiplied by 4 pi, which gives us 24 pi squared. So this is the theorem of Pappus. Courtesy of Connor and Corbin. So that's a physics way that you could do it. And of course we get the same answer. Better get the same answer. All right, let's get back to math. We are, where are we?
So the answer is 24 pi squared.
24 pi squared.
Yeah.
Yeah, funny volume. So, let's get back to the straws. Let's say we've got this region here. And when we look at that region, we recognize that it is vertically simple. It is not horizontally simple. It is vertically simple. So when we draw our vertical element at a random x, our vertical rectangle at a random x is vertically simple. The axis of rotation is over here. If we were to do a horizontal element, we could break it into 2 separate regions and use a horizontal element. But if the region is vertically simple, it's always going to be easier to use that fact. And when this rotates around, we are going to create a cylinder. And then if we puff up the cylinder a little bit, we are going to get a cylindrical slice. So the cylinder is like a cross section, and then when we add a little thickness to it, it's a cylindrical slice. And so we've got the nested cylinder idea. So regardless of these volumes, the idea is that we're creating a geometric shape that, when propagated, approximates the volume. But then we take the limit and use the Riemann sum idea. Take the limit as the number of, whatever they are, rectangles or disks or whatever. As the number goes to infinity, we get a better and better approximation. So there is the Riemann sum right there. And that Riemann sum, we get all these cylinders, we get better and better approximation. Take limit as n goes to infinity. And the limit of the Riemann sum becomes the definite integral. And that definite integral will give us the exact volume. So, when you look at this, we have a couple of things. We need to come up with a way that makes sense to think about this integrand. All it is the area of a cylinder. The area of a cylinder, circumference of the base, 2 pi r times the height of the cylinder, 2 pi r h. So 2 pi r is the circumference of the base, multiply it by height. So right here, this, without the f, so 2 pi r, let's use this, so 2 pi r. In this case, the radius is x. We'll talk about why that is. So this is circumference of the base. This is height right there. The function is going to give us height. We'll talk about why. So this whole piece in here is area of a cylinder, area of a straw. All right. So that's how we're going to get our cross-sectional area. Instead of a disk or a washer, we have a cylinder. Area of a cylinder is 2 pi rh. And then we just have to figure out how to put in the function. Here they've generalized it a little bit. The height of the cylinder that we're creating might come from two functions. So if we have some upper curve and lower curve, the height might be the upper curve minus the lower curve. We'll look at an example that should clarify that. Okay, so at this stage right now in our head, basic cylinder, area, circumference times the height. That's it. 2 pi RH. That's all that really we need to be thinking about in this moment. So let's see. All right. So we've got this region. It's going to rotate around the y-axis. It's going to create this bell-looking thing. Our cross sections are now a little weirder because they're nested. So if we take a random vertical element, because this region is vertically simple, that's a random vertical element at x. When it rotates around this y-axis, it's going to create a cylinder. That's the cross section. And then when we puff it up a little bit, when we add thickness to it, then it's going to be a slice, a cylindrical slice. We are going to use a dx. So that has not changed. Vertical element dx, horizontal element dy. That's always consistent. We always integrate perpendicular to the element that we selected, because this element is moving through, creating an infinite collection of nested cylinders. So, back to the basics again. Our shape is a cylindrical shell. You can call it the area of a cylinder, the area of a shell, whatever you want. Doesn't matter. Area in general for a cylinder, 2 pi RH. 2 pi RH. Circumference times the height. Okay, now we just have to figure out what the r and the h are in terms of our functions. We have one thing in our mind, though. We have a vertical element, so should we be integrating with respect to x or with respect to y?
X.
X, because we're going to have a dx. The thickness of that rectangle is dx. So that tells us when we replace this r with something, it must have x in it, no y's. When we replace the h with something, must have x's and no y's. So that is our check right there. We have to make sure that we know where we're going. Vertical element, we're going to x. These have to turn into x's, and that has to turn into x's. All right, so let's look at our picture. The radius. The radius is the distance from the element that we're integrating to the axis of rotation. Right? Everyone agree? If we've got two vertical segments, we're going to rotate one around the other. That distance is the radius of the cylinder that we're going to create. Can somebody tell me what that is in terms of x? Remember, we want to write it in terms of x.
Could be anything from 0 to 2.
Anything from 0 to 2. And what do we use to represent anything from 0 to 2?
X.
X. Right there, right? If we want it, this is a representative vertical element at a random x.
So
How far is that random thing from the y-axis? X. Right? That's what that x means. That's how far you are from the y-axis. It's exactly what it represents. So that x represents the radius of the cylinder at x. So that part's easy.
So r equals x.
R is equal to x. That's how far we are from the axis of rotation, is that x. Now height is a little more complicated, but not that complicated. Now we're measuring vertical. So the weird thing about shells is that we have a vertical piece and a horizontal piece. But both of those have to be in terms of x. We need to write both of those in terms of x. So what is the height in terms of x?
So y equals, yeah.
It's the function, right? 1 over 1 plus x squared. That is the height. This represents that vertical distance from the x-axis up to the curve. So that is going to be the height, 1 over 1 plus x squared. So now we have the area of the cylinder at x. And if you look at that formula that we had on the other page, it said 2 pi x. That's why there's an x, because the x is the radius when we draw a representative rectangle. So if we simplify this a little bit, we're going to have pi. I'm going to write it this way. I'll tell you why in just a second. Why I'm putting that 2 in the numerator. Volume is the integral of area. Volume is the integral of area. And we were told that we're going from 0 to 2 on the x-axis. So this is our integral that represents volume. That is the volume of that solid object. Now, again, you only have one integration technique right now. It's u substitution. Typically, we let u be what's in the square root, what's in the angle, what's in the exponent. And in this case, if we let it be what's in the denominator, we will get it. So this is going to be our u. It is not linear, so there's no reverse chain rule. We're just going to let u equal that. What is the derivative of that? The integral would be inverse tangent, but the derivative is just 2x. Isn't that the numerator? Let's go back to Calc 1 for a second. This you probably weren't told in Calc 1, but it is true. You know this from Calc 1. What's the integral of 1 over x? ln of absolute value x plus c. What was probably not pointed out is that the relationship between the denominator and numerator here is that the numerator is the derivative of the denominator. If we do this in general, if we put a function down here and put its derivative up here, and you use u substitution, you will get this. If you have the integral of a fraction, and the numerator of the fraction is the denominator's derivative, you will get natural log of the absolute value of the denominator, just like you did here. Why? Because if you let u equal f of x, then du will be f prime of x dx. You take the derivative, du dx, of both sides, and then move the dx to the right. And now look what happens when you substitute this back in here. So then this gives us the integral. F prime of x dx is du, so you end up with just du over u. U is the denominator. This gives us natural log absolute u. Then we back substitute, u is f, so we get natural log absolute f plus c. So we, in this class, are going to call this log form. And you do not need to go through these steps of integration every single time. If you need to do it a few times to get in the habit, great. But as soon as you recognize, this is how I will do it in this class, I will say, I'll put like an LF right here because it's in log form. And if you know that it's in log form, you instantaneously are going to get natural log absolute value of the denominator on the interval 0 to 2. It's automatic. Here we just did it in general. So if you have this situation, and it doesn't matter, like for example, let's suppose we have the integral, let's put a function down here. Let's put sine of x plus x squared dx. The derivative of this is going to be cosine of x plus 2x. So if you have that, it's in log form. If the numerator is the derivative of the denominator, it's in log form. And whenever we have log form, this is going to be natural log absolute value of the denominator. Automatically. Because of this. Right here. If you let u be the denominator, then du becomes the numerator. And the integral of du over u is natural log of absolute value of u. So it's always going to be that way. So this is where we're at. plug in our limits of integration. So we get natural log of 4 plus 1, which is 5. We don't need the absolute value because that's a positive number. Minus, what happens when we plug in 0?
E.
Say again?
You get E.
Not quite. You get if you plug in 0, you get natural log of 1. And natural log of 1 is? You told me earlier, Daniel.
0.
0. Right? If you think about the function, if you think about the graph of your function, your natural log function, right? Natural log function looks like this. And it's going right through 1. So natural log of 1 is 0. So this would be, if we wrote it out, this would be pi multiplied by that. Natural log of 1 is 0, so we'd end up with pi ln 5. Because this is equal to 0. All the algebra, all the trig. All right, any piece of that you want to ask about before we do a second example?
Could you scroll down to the bottom? There's a couple of things I didn't get down.
So our general principles are consistent. We have a solid object. We find a cross-sectional area, whether it's a disk, a washer, or a cylinder now. Integrate that cross-sectional area. That will give us the volume of the solid object. So that is where we are at. So let us find the volume using a cylindrical shell here. So when we look at this generating region, we first ask ourselves, is it horizontally simple or vertically simple? And we could try to force get disks or washers, but if you just go with the region and you look at this, you would say to yourself, oh, this is horizontally simple. It's not vertically simple because you would have two separate upper curves. Right? But horizontally, you've got a consistent left curve and a consistent right curve no matter where you drew that horizontal line. So we have a horizontal element. We have a horizontal axis. When you rotate, you're going to get a cylinder. All right. So let's label some things. This is a random horizontal line. So random horizontal lines are at a random y. Fair? Random verticals are at a random x. This line segment is rotating around the x-axis. The distance to the x-axis is going to be the radius of the corresponding cylinder. Okay? And this horizontal distance that measures the length of that red segment, that will be the height of the cylinder. So we're creating a cylinder that's lying on its side. So the height is horizontal, the radius is vertical. All right, so then we're saying to ourselves, okay, well, the area of a cylinder is 2 pi RH. We want to turn the R and the H into expressions with which letter? Y. Y, exactly. Because this is a horizontal element, the thickness is dy, which means our integral will be with a dy. It'll be an integral with respect to y. So we need to turn the r and the h into y's. So now we come look at our picture, and we first start with the r. What is r?
Y.
Y! The letter. Yeah, right? Because this distance here is what y represents. Y represents the distance from the x-axis up to this red line. So the radius and y are identical. And this distance is y. So that'll be our radius. And then our height is going to be this horizontal red segment's length. Now we're horizontal. Horizontal is always the right x minus the left x. So we look at this. Oh, these functions aren't presented as x values, so we need to flip them. We're going to add x to the left. We're going to subtract off the y. We'll end up with that as the right function. This function up here, we square both sides. We'll get x is equal to y squared. So we write both of those as functions of y, aka x values. We isolate x. It's horizontal, so we take the right x minus the left x, and that is our height. And just double checking, we can only have one letter in here in terms of x's or y's. Everything's matching. It's really easy to sort of make the mistake, oh, I want to subtract I want to do right minus left and just do 2 minus x minus root x. But then your letters are going to be commingled. So you just have to always have that check. If you're horizontal, you're going to have a dy. If you have a dy, these all have to be y's. Okay. Then we are going to integrate that area to get volume. So let's distribute the y. So we're going to have 2y minus y squared minus y cubed dy. And the y's coming from the y-axis will go 0 to 1. That's where this intersection point is up top. This right here is at 1. We didn't confirm it. We could confirm it really easily by plugging or by setting the square root of x equal to that. We could figure it out. It is going to be 1 though. Or you can just check even. If you plug 1 in here, plug in x equals 1, you get y equals 1. Plug x equals 1, you get y equals 1. So 0 to 1. 0 to 1 will be that. And we have a pretty basic integral here because it's polynomial, so we use our power rule. This will be y squared. This will be y cubed over 3. This will be y to the 4th over 4. 0 to 1. The 0 gives us nothing, so we just have to focus on the 1. So we're going to have 2 pi multiplied by 1 minus the 3rd minus the 4th. Common denominator will be 12. This is 12 over 12, so that's going to be a 12 in the top. We have to multiply by 4 over 4 here, so that's going to be minus 4 multiplied by 3 over 3. So we get that. So 12 minus 7 is 5, so we're going to get 5 pi divided by 6. And we can cancel out 2 right there. Any part of that you want to ask about? All right. So let's. Oh, come on! I can reach it. I should be using my other hand. All right. You ready to try one? Or should I do one more first? You ready, or you want to do one? Want me to do one more? Ready? All right, go for it. Let's go. Okay, so find the volume of this solid. We're going to rotate around the x-axis. So this curve right here, they've already isolated x for us, so that's cool. This x value right here, just note that that's 1 over root 3, which is root 3 over 3 if you wanted to rationalize. And there's y equals 1 to y equals root 3. And we are using shells, so we're going to use a horizontal integration element right there. And think of this at a random y value right there. All right, so see if you can set it up and integrate it. Find the volume of that thing. Whatever that thing may be. Let me know if you want a jab. So the first thing you want to write down is the area of the cylinder, area of a generic cylinder, pi r squared. And then from that picture, you want to figure out what the r and the h
2
are.
pi RH.
2 pi rh.
Not pi, yeah.
2 pi rh for area of a cylinder. Yep. Did I say something? Did I say?
Pi R squared.
I said pi r squared? Oh, that boy. Yeah, 2 pi rh, 2 pi rh, area of a cylinder. 2 pi rh. And then you want to discern what the r and the h are. Does anybody see what the radius is right off the top of your head? Radius is going to be... What was that? Anyone see what the radius is?
Is it y minus 1 over square root 3?
Way less complicated. Y. Yep. Wait. So this distance. So remember that the radius is nothing more than the distance from your representative rectangle down to the axis of rotation. That is your radius. Right, so this cylinder is on its side, and that distance and this distance are identical, correct? Right. So that y, whatever that random y is, that's representing the radius of your random cylinder. So the radius is simply y. And then the height is going to be that horizontal distance, the length of that segment. So that'll be right minus left. And they are very kind in this problem, and they already gave us that curve with x isolated. And we need that x isolated to do a horizontal distance. Mm-hmm. That is set up correctly. Yep. You don't even think, let me suggest one other thing first. Do you see a common factor that might cancel? What is the GCF of the denominator? What could you factor out of the denominator? Yeah. So if you factor a y out of the denominator, it's going to cancel with the y in the numerator. So that's right. Not quite. Not quite. If you, so you have a y in the numerator. Tell me your denominator again was.
Y plus y cubed.
So in the denominator, so remember that you can cancel common factors. So
Just cancels.
yeah, those just cancel.
Oh, got it.
Those just cancel.
So it's just y over y cubed.
Nope.
Four.
Yes. 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 That. Oh, so there, if you ended up with y over y cubed plus y, you could cancel a y out across the board. Because there's a common factor of y there, which would then cancel with the y that's in the numerator. And then this is going to pull from Calc 1, integral, I think Richard said it earlier, the integral of 1 over 1 plus y squared would be arctan of y. All right, let's go ahead and start writing it all out. So the area of a cylinder, 2 pi RH,
That's right. Yeah. It's like, how does the 4 go?
Yeah.
They still have minus y over root 3. What the hell? It's like that.
Ah!
Would that just be
What is that, 1 over root 3?
No, that would be 5 over 3.
Okay, so I did get that.
So does everybody agree with that part?
Yes. Okay, that makes sense.
So that horizontal length, that horizontal distance is right x minus left x. They gave us the right x. The left x is just this constant 1 over root 3. So we have that. Now when we distribute this y, we're going to have 4y divided by y plus y cubed minus 1 over root 3 times y. We could put that in the numerator. So we have that. And right here we have a y that cancels. In that first expression, there's a common y top and bottom, so those can be wiped out. Cancel common factors. So you're going to have 4 over 1 plus y squared minus y over root 3. All right, so now that is the area of the cylinder at y. So you plug some y value in between 1 and root 3, and that's going to be the area of the corresponding cylinder. Volume is the integral of this. And the integral of this, we are doing a dy between 1 and root 3. So 1 to root 3 will be our limits of integration. So for all this stuff. So there's our volume. So someone mentioned earlier, there's a Calc 1 integral that you learn. That's for arctan. It's one of the most important arc functions you're going to see. And we know that the integral of 1 over 1 plus x squared, that's going to be arctan of x. So we're going to use that fact. We'll see that one quite a bit this semester. So this is going to give us, the 4 is a constant, so constants just filter along. So it's going to be 4 arctangent of y minus, that's just a polynomial, so y squared over 2, the constant just floats along, so it's going to be y over 2 root 3, y squared over 2 root 3, and then 1 to root 3. Okay. Everyone all right with that? So, I'm going to draw a couple of things on the unit circle over here. When we plug in the upper limit of integration, we're going to have to evaluate an inverse trig function. So, inverse tangent of root 3, that says, so anytime you see an inverse trig function, inverse sine, inverse tangent, inverse cos, whatever, the first word that should come into your brain is angle. Inverse trig functions are angles. So when we plug in root 3 right there, inverse tangent of root 3 is the angle that has a tangent value of root 3. When you see a root 3, you should be thinking of the 12-sector unit circle where everything, it's where all the root 3's are, right? In the 12-sector unit circle. This distance is root 3 over 2. The short distance is 1/2. So, when you look at that circle, can you tell me what the tangent value of pi over 6 is? What's the tangent of pi over 6?
1/2.
over root 3.
So I just heard it. 1 over root 3, is that what you said?
Yeah.
Right, so tangent is the y over the x. The denominators would cancel, so you get 1 over root 3, or you could write that as root 3 over 3. Everyone agree? Tangent at pi over 3 would be
Root 3.
just root 3, so I'm using m for slope. Right, if you do y over x, the 2's would cancel. Root 3 over 2 divided by 1/2 is multiplied by 2 over 1. The 2's cancel, so you get root 3. So, The tangent of pi over 3 is root 3. Tangent is slope. It's the slope of the line, y over x. Tangent down here is the slope, root 3 over 3. So up here, when we plug in root 3, inverse tangent of root 3 is the angle with the tangent value of root 3, which is pi over 3. So this will be 2 pi multiplied by 4 times pi thirds. And then we plug in root 3 over here, and we end up with root 3 over 2. If root 3 goes in here, there's 2 root 3's now. It's root 3 times root 3. One of them will cancel. So we get root 3 over 2. So that's the upper limit plugged in. Now we go for the lower limit. Ooh, arctan of 1. Arctan of 1 is the angle with a tangent of 1. Tangent of 1 bisects quadrant 1. That angle is pi over 4. So plug that in there, the lower limit there. So 4 multiplied by arctan of 1. Arctan of 1 is pi divided by 4. And we're subtracting. So that's going to be negative, but then this is going to be positive. Plug in a 1, and we get 1 over 2 root 3. So that is our evaluation. That's where we're at. So let's see if we can simplify this mess.
Because he just distributed the negative to the right side. Because we're subtracting from that right side, so you would have to distribute negative to all the terms on that side.
All right, so to combine these, I'm just going to do that first. Put this, rationalize that, simplify a little bit. What's our common denominator going to be? 6. So we're going to have 2 pi. We're going to have a big fraction with a 6 in the bottom. To make that a 6, we have to double top and bottom, so that's going to be 8 pi. To make that a 6, we have to multiply top and bottom by 3. To make that a 6, we multiply the top and bottom by 6. That already has a 6. So that's what we have. 2 cancels with the denominator there, giving us a 3. And then we're going to have 8 pi minus 6 pi, which is 2 pi. Negative 3 root 3, add 1 root 3, we get negative 2 root 3. And we have that. And there's not much else we could do. We could just factor out the 2. So we could write this as 2/3 pi, or 2 pi over 3, does not matter. 2 pi over 3 multiplied by, when we factor out that 2, we're left with pi minus root 3. So that would be our simplified answer. All the algebra, all the trig. Practicing your inverse trig functions would be smart, because we are going to see a lot of inverse trig functions. When you're doing your homework, practicing all the algebra to the end. So keep in mind that this is an exact answer because we left the pi symbol, we left the square root of 3 symbol, we didn't type it into our calculator. Going all the way down to your simplest exact form is very, very good practice. In math, we always assume that we want an exact answer, not an approximation. You're only going to go to your calculator and get an approximation if it says find the approximation to the nearest decimal or whatever, nearest 2 decimal places, whatever it is. If there's no indication whether you should approximate or not, you always assume exact. And exact means that you leave the symbols. You're not putting in 3.14 for pi. So you leave it. Leave it as is. All right, let's try one more here where we're going to rotate. We're going to up the ante right out of the gate. We're rotating around x equals -2. So our axis of rotation is not a coordinate axis. It's that. Now our shape isn't too crazy. Y equals x squared, x equals 1, y equals 0. And we see that the vertical element, this is both horizontally and vertically simple. So you could use a a vertical element and create a cylinder, which is what we're going to do. You could actually use a horizontal element and create washers. You could. You'll get the same answer, of course. So let's go with the cylinder. So the area of a cylinder is 2 pi RH. Let's draw the R, draw the H. Oh, I already drew the R, right? That distance right there, that's R. This is our random vertical element at X, and the height is whatever the height of that vertical rectangle is. So, first off, are we using dx or dy? Dx. If we draw a vertical element, it's at a random x. If we have a random x, we're using dx. And what is R in this case? So remember, look at this picture. X is measuring that distance right there, right? X is measuring the distance over from the y-axis, so it's what?
X minus 2.
Close. X plus 2, because this distance is 2. Right? And now if we go back to our basic principle, horizontal distance, right x minus left x, the right x is x, the left x is negative 2. So if we did x minus minus 2, we'd get x plus 2. The more geometric visual way to do it is that, oh, this distance is 2 right here. This distance is x, so the total distance would be x plus 2, distance being non-negative. So you can think of it either way. And then your height is vertical, and it's whatever the function is, which was x squared. So there is our cylindrical area. And then the volume, once we have the area, the volume's pretty easy because we just integrate. We just have to make sure we have the limits of integration right. I'll distribute this x squared, giving x cubed plus 2x squared. The limits of integration come from our region sliding across from 0 to 1. So we're going to have 2 pi multiplied by, when we use the power rule here, we add 1 to each exponent, divide by the new exponent. So we will have 2 pi multiplied by a fourth plus a third. Common denominator of 12, we'll get a 3 and a 4, so that's 7. So we will end up with 7 pi divided by 6. All right, questions on any of those steps there? Oh, I have a question. Where did the 2 go in this numerator? I have a question. That should be a 2. If we plug in the 1, we get a fourth plus 2/3. Common denominator is 12, so we're going to multiply by 3, so we're going to get 11 there. And so that's going to be 11 pi over 6. 3 plus 8. Any other questions that you can think of with that one? 10, 9, 8. We're close. Should I give you a free? Oh no, time's up. I was going to give you some seconds. Right? Don't we end at 45? Would have been nice. Yeah. Stared there for a second. It's like, wait, we didn't end at 11:30, did we? No, definitely not. There's no way you guys would sit here for 15 minutes if we ended at 11:30. There's no way. But if we're supposed to end at 12, we can tell me. Sorry, you didn't get the lines already? Oh, not yet. Oh, you're coming here tonight.
I really have to set
Oh, maybe I was here. Maybe I was here.
Good luck. I will say this, I'm like 3 colleagues away from
All right, I'm sticking around. Ready to do some math. Oh, let me hit the pause on this recording.
Good to know, because that's, I mean, I got it.
That does not want to take that input.
That's what it is. Is that like the concepts?
There we go.